Hello, welcome to another video of this video series. So today I'll be talking about the focused ion beam technique as well as transmission electron microscopy, commonly abbreviated as TEM. So my microphone is a bit funny, so I hope that this recording will turn out okay. So let's dive right in. So firstly, right, maybe it's important to first emphasize that because TEM involves transmitting an electron beam through a sample, there is a maximum sample thickness that can be analyzed using TEM. And so normally, the sample must be a few tens to a few hundred nanometers thick in order to be transparent to electrons, such that electrons can be transmitted through the thin sample and be detected, the image be detected by the TEM. And so how this normally is done is that the thin sample is loaded onto a copper grid, and this copper grid is then loaded into the TEM machine. And this copper grid, of course, there's like spacing within the grids, and the electron beam will then go through one of these spacings where the sample is actually placed such that it passes through the sample and not the copper lines. And so the common use of TEM is actually to obtain the cross sections of certain devices. Because the sample required is thin, so we can cut a thin cross section of your device and actually image it under TEM to observe the various features of your device. So an example would be, let's say, this kind of cross section of your device, so you can really see all of the metal layers, right? Going up from probably the contact layer all the way up. And you can see that the pitch as well as the space, the width of the metal lines are getting larger and larger as we move up from the contact layer all the way up to the last metal. And because TEM's resolution is extremely good, we can also image extremely small features such as the transistor itself. So an example over here is, as you can see, we can image directly the transistor. We can see the epitaxially grown silicon germanium source and drain. So the use of the silicon germanium is actually to create a certain strain on the channel to improve the charge carrier mobility. And you can see the gate, right, the source and drain contact, so on and so forth. Okay. And how do we actually obtain this cross-section sample? So we need a way to actually excise a very thin cross-section out of the bulk sample, and the way we we do it is using the focused ion beam. So you can think of the focused ion beam as a very precise, like, medical scalpel that is being used to actually cut a very thin slice of the material out of your sample for the TEM imaging. And so the FIB instrument is actually based on using a very highly energetic ion beam. So normally the most commonly used is the gallium ion beam. And so this acts like a medical scalpel to cut through the material. And so the way that this ion beam cuts through this material is by sputtering out the material present in the sample, thereby achieving a cut to the material. And so the instrumentation of the FIB actually includes not just your beam of gallium ions and your very expensive ion source, but also an SEM, so that a high resolution image of your sample can be obtained as it is being cut. And this is very important because you need to know where you are cutting, how deep you are cutting, as well as making sure that the sample is not undergoing excessive damage from the ion beam as you are cutting it. And so that is the use of the SEM to obtain the imaging of the sample as the excision of the cross-section is being obtained. And in addition to using the gallium ion beam to remove material from the sample, thereby achieving a cut through the sample, it can actually be used to deposit things on the sample as well. For example, if you were to introduce a gaseous precursor of platinum, right, and introduce it into the chamber, the area that is actually being illuminated, so to speak, the area that the ion beam is incident on, there will be a chemical decomposition of your platinum precursor, and thereby achieving the deposition of a thin platinum layer on your sample surface. So there's actually two modes of operation of your FIB. One is the ion milling mode, which you can think of as a cutting mode, right, or the digging out of material mode. And the other mode is the deposition mode, where the ion beam actually decomposes the chemical precursors of materials such as platinum, thereby allowing the deposition of a thin layer of platinum, or it could be gold, it could be carbon, right, on your sample surface. And so you may think, what is the purpose of deposition, right? Aren't we trying to cut it, right? The purpose of it is actually to protect the sample being cut, right? Because we want to cut the sample, yet we also don't want to damage the sample excessively from the ion beam. Because if, let's say, your ion beam being a very highly energetic source of energy, it can actually cause the degradation of the material in the sample, the amorphization of crystalline materials, and therefore causing you to lose very valuable sample information as you're doing the cutting. So we don't want that. So this deposition allows us to actually deposit a protective layer to protect sensitive top layers of the sample as it is being cut. So let's look at the example, right? How all of this is being used to obtain a cross-section sample for your TEM analysis. So firstly, a capping film is deposited using the deposition mode that I told you earlier, and this is so as to protect the top layer of the material as the trowels are being cut on both sides. So in the first step, right, basically a very deep trench, right, I can think of it as a trowel or a trench, is being cut on one side of the sample. And then after that, the sample has to be rotated and it has to be cut on the other side as well. So essentially, we are cutting two deep trenches on each side to isolate the thin cross-section, right? And then after that, we need to find a way to get this thin cross-section out. So you need to insert the manipulator. You can see you insert the manipulator, and we do a welding. Welding, once again, is done by deposition. So you deposit some material to stick the cross section that's basically jutting out of your sample to your manipulator, right? Then after that, you can do a complete isolation of your cross section, cut it out completely, and your cross section is stuck to your manipulator, right? It can be plucked out, and further treatment can be done, such as polishing the edges of the sample of the cross section that you've cut out, and this has to be done on very low ion energy setting so as not to damage the very thin sample. And final polishing can be done, right, to make sure that the sample is as thin as possible, because if you were to do things like lattice imaging through a HRTAM, it's often benefited from a thin sample. Okay, and another use of FIB, right, in addition to the conventional use of obtaining the cross sections for TEM imaging, is for device delayering. So the FIB, being an ion milling technique, can be used to mill away, to sputter away the material in your device layer by layer, thereby allowing us to peel back each layer of the device. And so there can be multiple purposes of this. Firstly is in fault identification. So imagine if you have your device with all your interconnect and your dielectric layers all the way on top, and your fault is somewhere inside. Like maybe it could be in the first few metal layers, it could be in the contact layer, it could be even in the device layer. There's no way you'll be able to directly image the area of the fault without removing the material that is at the top of your chip. So the FIB can then be used for device delayering, such that we can finally reach the area where the fault is located, and a high resolution electron microscope image can be obtained of the defective area. Right. And another purpose is also to do some form of like investigation of, let's say, chips that are obtained from a certain company. So it's quite common nowadays, especially with the very competitive semiconductor industry, for various companies, analyst teams to actually obtain the chips of certain companies, well-known market leaders, and do a certain tear down to analyze what are the kind of structures and architectures being used in those chips. And basically the FIB can also be used for such purposes. Right? So before I talk about TEM, I would like to first talk about what are the contrasts and the differences between SEM and TEM. So while SEM involves scanning an electron beam on the sample surface and detecting the electrons basically reflected off the surface of the sample, and this are both secondary electrons and backscattered electrons, right? TEM, in contrast, right, passes the electron beam through the sample and uses the transmitted electron beam to form your resultant image. Okay. And so the general structure of your TEM looks something like this. Once again, you need your electron source, you need your anode to accelerate the electron beam to the high enough accelerating voltage, normally about, let's say, 20 kilo electron volts for a standard TEM used in semiconductor industries. And then after that, a series of electromagnetic lenses to basically shape and focus the electron beam. And then the very thin beam is then passed through the sample, right, and then pass through the objective lens aperture. And so there's basically, if your sample, right, is a crystalline in nature, basically you realize that the sample itself acts like a diffraction grating. So the incoming electron beam acts like your incoming light source, like your laser light in a secondary school experiment, and your sample acts like the diffraction grating in the experiment, and you will see series of diffraction patterns, right, of the beam that's passed through the crystalline material. Because you can imagine that a crystal lattice, right, consists of basically regularly spaced atomic planes, and so obviously this can act as a gigantic diffraction grating that will help to cause the interference of the incoming beam and the formation of a diffraction pattern. And so, of course, in the diffraction pattern, there will be various maxima, and the light from, or rather electron beam from any of these maxima can actually be used to form the resultant image. So basically, each of these maxima, if you were to allow the beam to diverge and then capture it in the image plane, it basically can form an image of your sample. Okay. And so, yeah, as mentioned earlier, basically the sample, if it's crystalline in nature, it acts as a gigantic diffraction grating, and therefore allowing for the formation of diffraction patterns in the back focal plane of the TEM. And so, depending on the kind of crystallinity in the material, if it is single crystalline, you obtain basically a single crystalline-like diffraction pattern. If you're polycrystalline, you tend to see basically a bit more like ring-like diffraction patterns, and you can think of it because a polycrystalline material consists of many grains, and each grain has the crystal lattice in a different orientation, in a different angular orientation. So what happens if you take the diffraction pattern of a single crystalline material, and then you superimpose many of these but tilted at different angles with respect to one another? What do you end up getting? You end up getting pretty much like a ring, right? Like a ring of diffraction patterns. So this is what you observe in a polycrystalline material. And if you have an amorphous material, for example, quartz, right, silicon dioxide, that is a completely amorphous material. There is no regular lattice spacing that can act as a regular diffraction grating. However, there will still be some form of diffraction, but in this case, it will be basically a more broader diffraction peaks. You'll not see like very clearly defined rings in the polycrystalline case, but you just see very how to put it, diffuse, very diffuse rings of light, so to speak. And so this is actually a very nice schematic showing how the basically the various atomic planes in a single crystalline material can act as a diffraction grating to form your diffraction pattern. And basically, if you are familiar with X-ray diffraction, it's basically the exact same principle, just that your standard XRD spectrum basically takes a section, right, along a certain, let's say, along a certain angle, and then basically plots the point in a diffraction pattern as basically your peaks in your XRD spectrum. So it's basically very similar or practically the same principle, just that one is using the electron beam as your so-called light source, and the other one is using your X-ray beam as your light source. And basically from the observation of the diffraction pattern, and this can be obtained from a TEM. Because if you choose to obtain the image from the back focal plane instead of the image plane, you will not get the image of your sample, you will get the diffraction pattern instead. And so you can obtain actually all of these diffraction patterns from a TEM instrument. And basically, if you observe interesting artifacts in your diffraction patterns, such as streaks, such as extra spots, right, that are close to each main diffraction spot, or you see like streaks at various angles, all this can tell us important information. For example, it can tell us about crystal twinning, it can tell us about the existence of multiple phases in the material, and so on and so forth. Okay, and of course, basically the kind of geometry that you observe in a diffraction pattern is related to the crystal structure of your material. So different unit cell structures such as your simple cubic, your FCC, your BCC, your monoclinic, orthorhombic, tetragonal structures will have different diffraction patterns with different geometries. So from the electron diffraction pattern, we can also obtain information about your basically your crystal structure of your material, what is your unit cell of this lattice structure, as well as the lattice parameters. Okay, so for example, this image over here shows the case for a HCP, right? Lattice, the diffraction pattern of HCP lattice when the incoming electron beam is has this direction. Basically, this is the zone axis of your diffraction pattern. So basically, if the incoming electron beam comes at different angles, of course, the resultant diffraction pattern will be observed to be different. So actually, this is a fairly technical topic of discussion. I would not actually go in depth into it, of course, but basically, if you know your fundamental relationships, right, between your real space and reciprocal space, and you do the resultant mathematical computations, you can deduce both the crystal structure as well as the lattice parameter from the diffraction pattern, as well as, of course, deduce your zone axis of this particular pattern. So as you can see, the HCP electron diffraction pattern and that of your FCC, right, the bottom one is your FCC, is different. So basically, the purpose of this slide is to say that materials with a different crystal structure will produce your diffraction patterns that has a different geometries. Okay, and so as I've mentioned earlier, we can actually use the electrons that come from any of the maxima to form your image in the image plane. If we use the electrons from the central maximum to actually form your image, this is called the bright field image. And why is this so? You can imagine area in your sample that is a hole, no material inside. Right, let's say it's a porous sample, there are such holes. Right, electrons that pass straight through these holes, where will they appear in? Will they appear in your higher order maxima? No, right? Electrons will not be scattered by nothing to higher order maxima. It will be present in the central maximum, right? And so that's why in your bright field image, holes appear bright, because all your electrons that pass through the hole will go into your central maximum, and now you are using the central maximum to form your TEM image. So how do you know that image is a bright field image? The holes are bright, right? And if you follow this logic, right, in the dark field image, when you are forming this image from a higher order maximum, from the electrons that are coming through from this higher order maximum, the hole will be dark, right? Because there is no material in the hole to scatter and diffract the electrons to higher order maxima. So when the image is formed from the electrons from the higher order maximum, we call this a dark field image, because areas where there's no material, where there's a hole in your sample, appear dark, so it's called the dark field image. So bright field imaging is the predominant mode for examining like microstructures of the material, such as you can see these grain boundaries and certain kind of impurities in the material. However, right, dark field imaging is also widely used to obtain an image with higher contrast, because you can clearly see these grain boundaries or grooves of grain boundaries, and these grain boundaries strongly deflect the incoming electron beam. Actually, it shouldn't be light, but the electron beam to the higher angles. And because the dark field image is formed from the electrons precisely from this higher order, higher angle maxima, these grain boundaries appear bright in the dark field image. Okay? And so, now that we have talked about the two main modes of imaging in TEM, which is your bright field and dark field imaging, it is appropriate to talk about the types of contrast in TEM. And so there are three kinds of contrast, right? Mass thickness contrast, diffraction contrast, and phase contrast. And so let's dive into it one by one. So mass thickness contrast, right, is actually very, very sensible. Like if you have a material of the same homogeneous composition, the thicker parts of the material, the thicker parts of the sample, right, they will attenuate the electron beam to a greater extent. Therefore, that part of the sample will appear darker in the resultant bright field image, right? That is a very logical conclusion, right? Because electron beam passing through a thicker part of the sample, right, assuming homogeneous material composition, electron beam passing through a thicker part of the sample will be attenuated to a higher extent. However, right, of course, when your sample is made out of multiple materials, right, things are not so straightforward anymore because different materials attenuate the electron beam to different extent. And normally that is correlated with the mass of the elements that is present in that part of the sample. So we call it basically mass thickness contrast. You can think of it as attenuation contrast, right? When there's a part of the sample with a greater thickness or higher mass, it attenuates the electron beam in the area to a much greater extent. Therefore, the area of the image will appear darker in the bright field imaging mode. And then the second kind of contrast is diffraction contrast. So let's say we are forming the TEM image from the as a bright field image, right, from the center maximum. Right? If there's a part of the sample that, let's say, has a single crystalline structure and is oriented in such a way that it strongly diffracts the incoming electron beam, right? Then the electron that passes through the area of the sample that is strongly diffracting will mostly be scattered and diffracted to a higher order maxima. So what will happen in your bright field image? These strongly diffracting areas of your sample will appear dark in your bright field image, right? Because the electrons that pass through that strongly diffracting area of your sample, not many of them will be present in your central maximum. A lot of them will be scattered and diffracted to a higher order maximum. Therefore, this area will appear dark in your bright field image. And then by that same logic, right, if you're following my logic here, then you can also see that these strongly diffracting areas of your image, strongly diffracting areas of the sample will appear bright in your dark field image, right, by that same logical argument. And in addition to diffraction contrast, basically forming bright and dark areas of contrast in the sample depending on how diffracting the material of the sample is in the area. This diffraction contrast can also be used to identify defects. So for example, you can see in these two images here that these locations in your crystalline sample appear as dark lines in your TEM image. And this is because the incoming electron beam, when it's incident on these locations, the incoming electron beam is diffracted to basically higher angles and not captured in the beam that is used to form the image. Right? And so this actually allows for the use of TEM to observe and identify these locations present in your material. And so this is quite important for, let's say, the case of identifying these locations in your transistor channel, right? Because in your transistor channel, if you have certain dislocations, they can form leakage paths, which will cause things like high subthreshold current and other undesirable side effects. So this shows the advantage of TEM in imaging things like transistors because you can identify these locations that would degrade your transistor properties. Right? However, it is not in every case that your dislocations and other such defects can actually be imaged in TEM. This is because if your displacement vector or the Burgers vector of the stacking fault is parallel to the beam that you are using to form the image, right? Basically, the electrons that are being scattered by your dislocations or your faults will be scattered in a direction parallel to your to your electron beam, and therefore it will actually basically still be collected. These scattered electrons will still be collected in that same electron beam that's used to form the image. And therefore, as you can see over here, when the beam that you are using to form the image is in this -220 direction, which happens to be parallel to the Burgers vector of your dislocations. The dislocations completely disappear from your TEM image. So you need to make sure that this condition is not satisfied in order to be able to visualize the defects in your TEM image. Okay, so lastly, the last type of contrast that I'll talk about is phase contrast, and I'll talk about how it is being employed in high resolution TEM. Okay, so basically what this image is trying to say is that the resultant image that is formed in the TEM comes not just from your sample, but also from the optical properties of your TEM instrument, right? So what does all this mathematical formula mean? Okay, so this basically tells you that the diffraction pattern that is being observed, right, is basically dependent on your crystal structure, right, of your sample. However, when you eventually obtain the image, right, the image, the function showing the image brightness and intensity is GK, is actually not just dependent on the crystal structure of your sample, but also dependent on something called the contrast transfer function, which is something unique to the particular optical system in your instrument, which is dependent on things like aperture size and geometry, the lens aberration, because even though these are electromagnetic lenses, they can have things like a chromatic aberration as well as the envelope function of your TEM instrument. So basically if I could summarize what this diagram is telling you in a sentence, is that the resultant image that is formed from your TEM is a convolution of both your material properties, your sample properties, as well as your optical instrument properties, your TEM instrument, your microscope instrument properties. And so how HRTM or high resolution TEM works is that it takes advantage of this dependence of your resultant image on both your sample crystal structure as well as the optical properties of your entire TEM. So in HRTM, right, the interaction of the electron beam with the crystal in your sample, right, the crystal lattice in your sample, produces transmitted and diffracted beams that have different phases, because of course when your beam interacts with your lattice and gets diffracted, right, they will undergo there'll be a different phase change, right, compared to the beam that's directly transmitted through your material. And so these beams can interfere in the image plane, right, producing basically interference fringes. That is basically the way that this phase contrast manifests itself. And if we tune the objective lens defocus, so the objective lens defocus is one of the parameters in your a contrast transfer function, because it is something that's dependent on your instrument setting. So if we change this objective lens defocus as well as tuning certain lens aberration parameters, because we can basically tune the property of the lens by modifying the electromagnetic field of the lens, right? Because these are not actual like glass pieces, right? These lenses are electromagnetic lenses which can actually be tuned. So if we tune the lens defocus together with the lens aberrations, we can basically create suitable imaging conditions such that the resulting fringes that are observed in the TEM image are highly correlate to the lattice spacing of the crystalline material, right? So basically, by tuning the imaging conditions being used in the TEM microscope, we can obtain this kind of nice fringes in your TEM image if your sample is single crystalline in nature, and the spacing between these fringes has a correlation to the spacing between the atomic planes in the crystal lattice. However, it's important to emphasize that this regular fringe spacing is not the direct imaging of the lattice planes in a sample. So these lines that you see here is not the direct images of your actual lattice planes in the material, right? But it's something that appears as a result of diffraction through the lattice and is correlated to lattice spacing. So oftentimes you have to do a certain kind of optical simulations to enable the matching of your resultant HRTM fringes to your basically your lattice parameters to obtain values such as your lattice constants of the material. Right, and so with this, I actually end this video on FIB and TEM. So I hope that this video has been useful to you. In the next video, what I will do is that I'll cover SIMS, which is secondary ion mass spectroscopy, as well as potentially I'll also cover XPS, X-ray photoelectron spectroscopy. And yeah, so I hope you enjoyed this video and see you in the next video.